So continuing the analysis, in the previous clip we had derived the expression for FM when modulating signal is a single frequency signal in cosine form. This is how the expression looks like. If I write the expression in the form of frequency in hertz, then I will replace omega c with fc, which becomes 2 pi fct plus mu f sine, and omega m, I'll replace omega m with 2 pi fm, where fm is modulating frequency in hertz. So that becomes my complete expression of fm signal for single frequency sinusoidal signal. Now let us quickly define few important parameters. The first parameter that I'm going to define is called frequency deviation. We will denote frequency deviation with notation delta f. Its definition goes something like this. Frequency deviation is defined as the maximum departure of the instantaneous frequency from the original carrier frequency. When I say instantaneous frequency, we write it using a small letter f, and carrier frequency is nothing but fc. I'm taking frequencies in hertz. We are talking about departure of f from fc. That means we are talking about the difference between f and fc. This represents the departure of instantaneous frequency from the carrier frequency. The maximum value attained by f minus fc will be my frequency deviation. So delta f is nothing but the maximum difference between f minus fc. So let's say fc is, for example, 10 megahertz, and when you are changing carrier frequency fc of 10 megahertz towards upper and the lower side, and let's say for example the maximum frequency it goes up to on the upper side is 10.1 megahertz, and hence on the lower side it will go up to 9.9 megahertz. So that's the range over which instantaneous frequency of FM signal will vary. Now this simply means that at any given point of time, if you read the frequency of the FM signal, it will be a value between 9.9 megahertz to 10.1 megahertz. Please note that that doesn't mean the bandwidth of the FM signal will be from 9.9 megahertz to 10.1 megahertz, because right now we are talking about instantaneous frequency at some particular time instant. The actual bandwidth can be calculated only by expressing signal in frequency domain. We'll do it later on. So I repeat, f minus fc in the example that we have taken, on both the sides maximum will be 10.1 minus 10 megahertz or 10 megahertz minus 9.9 megahertz, which becomes 0.1 megahertz. So my frequency deviation in that case will become 0.1 megahertz or 100 kilohertz. Now let us find out the expression of f minus fc for the FM signal that we have written. So we first need the instantaneous frequency. To get instantaneous frequency in f, we'll have to start with the instantaneous frequency in radians per second, omega, which we obtain by performing operation of d theta by dt, where we differentiate the angle of the modulated waveform, which right now is in the form of 2 pi fct plus mu f sine 2 pi fmt. It is available here. So when I differentiate this whole angle, it becomes 2 pi fc plus mu f. It's a constant, so it will remain as it is. The derivative of sine will be cosine function, and whenever you differentiate, you multiply by coefficient of t. So that becomes 2 pi fm. That's the coefficient, and derivative of sine will be cos 2 pi fmt. So that's my omega. Now let us divide throughout by 2 pi. If I divide by 2 pi, omega by 2 pi will become f, which is the instantaneous frequency in hertz. We already have 2 pi here, so 2 pi will cancel out. When you divide by 2 pi in the second term, again 2 pi will cancel out, so it becomes mu f into fm into cos of 2 pi fmt. This gives me the departure f minus fc, the departure of the instantaneous frequency from the carrier frequency. It becomes mu f into fm into cos of 2 pi fmt. And now we can derive the expression for delta f. So delta f for frequency modulation comes out to be, it is maximum of f minus fc, and f minus fc is this whole thing. So it will be maximum of mu f into fm into cos of 2 pi fmt. Now we all know that the maximum value taken by cosine function is equal to 1, and therefore we get delta f equal to mu f into fm. Very important expression of frequency deviation. Or I can also use this expression to define modulation index mu f. Mu f comes out to be the ratio of delta f and fm. So we get one more important expression.